YouTube. మేడం గారు కనిపిస్తున్నారు, భారత మేడం కనిపిస్తున్నారా? Good morning, madam. Shall we start, madam? We are live on YouTube now.
Yes, good morning.
Yes, yes. So, dear all participants for this webinar on interpretation of spectra, that is from molecular weight to chemical structure. We at Sri Adi Chunchanagiri College of Pharmacy, Faculty of Pharmacy and Department of Pharmaceutical Chemistry and Analysis are organizing this webinar for enlightening spectral interpretation knowledge for the upcoming students and faculty. And with this introductory note, I would like to request our principal, Bharati Madam, to give opening remarks for today's webinar.
Jai Shri Gurudev. My humble pranamas to Parama Puja Jagadguru, Shri Dr. Balagangadharanatha Mahaswamiji and Parama Puja Jagadguru, Shri Nirmalanandanatha Mahaswamiji. A warm welcome to one and all who are participating in this webinar. And from Sri Adi Chunchanagiri College of Pharmacy, which belongs to Adi Chunchanagiri University, I would like to give highlights about Sri Adi Chunchanagiri College of Pharmacy. Adi Chunchanagiri College of Pharmacy is since 43 years. Growth of Adi Chunchanagiri Pharmacy College is predominant and achieved status of one of the premier institution with NBA accreditation, NIRF ranking constantly since 5 years. And Sri Adi Chunchanagiri College of Pharmacy is also ISO certified, and many other quality initiatives are initiated in Adi Chunchanagiri College of Pharmacy. Today's webinar, it is national webinar on interpretation of spectra, molecular weight to chemical structure. And I welcome Dr. A.E. Prabhar sir for the seminar.
Thank you, madam.
Once again, I welcome each and everyone to the webinar. Please.
Thank you, madam.
Thank you, sir.
So with this, let me try to start our session with the introductory note of our speaker, Dr. A.E. Prabhakar. He is having 24 years of experience, out of which 20 years falls under academics. He worked under various positions, starting from assistant professor to HOD at various institutions. And apart from this, he is having a very good profile, like published 50 indexed journals, 7 Indian patents, one book chapter into his account. And apart from this, he also did one UGC minor research project. He guided 40 PG scholars and 10 PhD scholars. He is having membership in various professional bodies in India, and he is also expert in various accreditation process, and he served as resource person in various conferences and FDPs. This is only very short profile of his. Uh, this is not the entire profile. If I want to tell his entire profile, it may take more time. So I won't want to lag this. So with this short introduction of our speaker, I would like to request our speaker to start his session. Prabhakar sir, please start your session, sir.
Thank you, sir. So first, I would like to welcome everyone for this seminar. And before starting the seminar, I would like to thank Dr. Bharati Madam, Dean and Principal Adi Chunchanagiri College of Pharmacy, for giving me this opportunity. And I would like to thank Dr. T.Y. Pasha also, the HOD, Department of Chemistry, Adi Chunchanagiri College of Pharmacy, and K. Naga Prashant, Associate Professor, Adi Chunchanagiri College of Pharmacy. So, sir, shall I share my screen?
Yes, sir. Please start sharing, sir. Sir, am I audible?
Yes,
Yeah,
you are audible.
please start sharing, sir.
Is it visible, sir?
Yes, sir. Done, sir. Your screens are visible. You can go ahead, sir.
Okay. Good morning, all. Today we are going to discuss about how to interpret the spectra and how to derive a organic structure from reading the spectra. So the main aim or objective of today's session, if you see this spectrum, we have different spectrum for a single compound. It is the spectrum for a single compound. We have the top, we have IR spectrum. Here we have IR spectrum, and we have a UV spectrum, we have mass spectrum, and we have a proton NMR spectrum. And if you see all the spectrum, we have so much information, or we get so much information from the spectrum. By keeping all these values or all the information, we can derive the molecular structure or the chemical structure of the compound, and that is what we are going to discuss today. So I just say that I am not going to discuss about any principle or instrumentation. We are mainly or keenly into the interpretation of the spectrum. Okay, so before going into this spectral analysis, we'll discuss little bit every spectroscopical technique, then we will get into how to read the spectrum. So as I told that at the end of the session, we would like to, or we are trying to write a chemical structure for this compound. So this is the spectrum for a single compound. We will see later. So before getting into this, we must know what you mean by spectroscopy. So spectroscopy, we all know that is the study of the interaction of electromagnetic spectrum or electromagnetic radiation with the matter. So the electromagnetic radiation is going to interact with the substance, and it is going to give the spectrum. So now what is electromagnetic radiation? Electromagnetic radiation, it is not the single wavelength of radiation. It comprises many radiations put together. We have given the name or it is given the name electromagnetic spectrum. What are there? We have a gamma rays, X-rays, UV, visible, IR, microwave, and radio waves. All these radiation together, we say it is a EMR spectrum. So in this, we have the high energy radiation like a gamma radiation and the low energy radiation like a radio waves. When these radiations are going to interact with the substance, we are going to get the spectrum. So what are the different interactions are possible? Sometimes the EMR can be absorbed by the sample, or sometimes after absorption, the sample may emit the radiation. So based on that, we have a different spectroscopical technique. One, we can say it is absorption spectroscopy. The another one is a emission spectroscopy. Sometimes the compound may not be able to even absorb, or sometimes they don't emit, sometimes they scatter the radiation. So we have a nephaloturbidometry. So based on that, we have different spectroscopical technique. We have a UV visible spectroscopy, infrared, IR spectroscopical technique, and if you use a radio wave, it is a NMR spectroscopy. And one more thing is that every compound, that means all the compound cannot interact with all the radiations. For example, if you take a methanol, simple compound, if you take a methanol, the methanol can, that means it is not having the capability to interact with the gamma rays, X-rays, ultra visible, all the radiation. That means it can interact with only some specific type of radiations. So which will decide the interaction? Because we need some structural requirement for a compound to interact with any type of radiation. For example, if we take a UV visible spectroscopy, if a compound have to interact with the UV visible radiation, the compound should have a chromophore. The compound should have a chromophore. Now, what is chromophore? Chromophore, it is covalently unsaturated group. Covalently unsaturated group, which is responsible for the absorption of UV visible radiation. If a compound doesn't have the chromophore, we can say that we are not going to get much information about that particular compound in UV visible spectrum or UV visible spectroscopy. So what do you mean by chromophore? We told that it is a covalently unsaturated group. What do you mean by covalently unsaturated group? There should be two double bonds, minimum of two double bonds. These two double bonds should be in the conjugation. What do you mean by conjugation? One double bond is going to be separated by one single bond, then double bond. Means two double bonds are separated by one single bond. It is a conjugated double bond system. Conjugated double bond system. So if a compound is having conjugated double bond system, then this compound will give the UV spectrum. Okay, clear? So what do you mean by conjugated double bond system? We told that double bond, single bond, double bond. This conjugated system either may be present as an open chain. It is called as a acyclic diene. Sometimes this conjugated double bond system will be present in a cycle or a ring system. So in this, you can see that there are two double bonds. Both the double bonds are in a conjugation, but it is inside a single ring. Then it is called as a homoannular system. And here also you can see there are two double bonds. Both the double bonds are present in the conjugation, but they are present in a two different ring. Then that is called as a heteroannular system. Here we have a double bond conjugated with a double bond O. Here we have a double bond conjugated with a double bond O. Here also we have a double bond conjugated with a double bond O. So this type of system is called as a enones, or otherwise we can call it as alpha beta unsaturated compound. And lastly, there is another skeleton is required, or the structural requirement. The compound may have an aromatic ring. So the aromatic ring is a substituted aromatic compounds. We have two substitution. One is R, and another one is A. Suppose if the A is OH, then this compound will become a carboxylic acid, because it is aromatic ring, C double bond O and OH, it will become a carboxylic acid. Suppose if the A is a hydrogen, then it will become a aldehyde. and A is any alkyl group or aryl group, then it will become a keto. Okay, if A is any alkoxy group, OCH3, then it will become a ester. It will become ester. So what we need in a UV visible spectroscopy, if a compound have to absorb the UV visible radiation, the compound should have a chromophore. The chromophore may be either acyclic diene, the simple double bond, single bond, double bond system, or sometimes this system may be present in a ring. It is called as a, either it may be in the single ring, it is called as a homoannular. If it is in the two different ring, it is called as a heteroannular. Or otherwise, this double bond may be conjugated with the C double bond O, then it is called as a enol. Or sometimes this conjugation will be present as a in the aromatic ring structure. It is a substituted aromatic compound. So what we are going to see, if a compound is having the chromophore, it is going to absorb the UV visible radiation. In the compound, there will not be no chromophore. Sometimes or not sometimes, every time there will be oxo group. Other than chromophore, some groups will be attached with this. So what are oxo group? They are covalently, sometimes they are either saturated or they may be unsaturated group. They cannot absorb the radiation, but they can influence the absorption of chromophore. How it is going to influence the absorption? They alter the wavelength, or sometimes they alter the absorption. So they are going to alter the wavelength, or sometimes they are going to alter the absorption. Okay. So in the UV visible spectroscopy, when a compound having the chromophore and it is absorbing the UV radiation, there will be a electronic transition. There will be electronic transition. What are the different electronic transition that is possible in the UV visible spectroscopy? There will be different electronic transition. For example, we have N electron, we have pi electrons, we have sigma electrons, we have we have N electrons, we have pi electrons, we may have a sigma electron. So it is pi star and it is sigma star. So when a compound absorbs the UV radiation, if the compound is having N electron and double bond, it may go to N2 pi star. If a compound having the conjugated double bond system, it will undergo pi to pi star transition. So we are mainly concerned about this transition, pi to pi star transition. If a compound having the conjugated double bond system, then this type of compounds will undergo pi to pi star transition. So how can we understand whether the compound is undergoing N2 pi star or pi to pi star transition? Or sometimes if it is the compound is made up of that means it is having heteroatom and it is having only single bond, then that type of compounds will undergo N2 sigma star transition. But we are not worrying about the N2 sigma star transition. We are concerned about the pi to pi star transition and the molar absorptivity value. So there is a value, it is a constant. If the molar absorptivity value, if you are getting more than 10,000, if the value goes more than 10,000, it indicates that your compound is having conjugated double bond system, or we can say that it is because of the pi to pi star transition, pi to pi star transition. So at the end of the day, whenever you scan a compound, you are going to get a UV spectrum. You are going to get the UV spectrum. What information we get out of this UV spectrum? We say that by keeping this absorbance, if you calculate the Emax value, that means molar absorptivity value, if it is going more than 10,000, then you say the compound is having the pi to pi star transition, or we can say that the compound is having the conjugated double bond system. Or otherwise, what we discussed, it is a electromagnetic radiation. It is going to interact. When it is going to interact with the UV visible, the compound need a chromophore. The chromophore may be a acyclic diene, or may be a homoannular, or maybe a heteroannular, or maybe a enone, or maybe aromatic compound. Whenever it is going to absorb, it is going to undergo the pi to pi star transition. If the pi to pi star transition is there, the Emax value is going to be 10,000. This is what we are going to get the information in the UV visible spectrum. See, so if when we go in deeper and deeper, we are going to get more information about the molecule. For example, in the electromagnetic radiation, we told that we have a visible rays, we have a UV rays, then comes the infrared, because the energy of the infrared is going to be less, and the microwave is lesser than that, and radio wave is lesser than the every radiation, because it is the least energy radiation. When the energy is going down and down, the information about the molecule is going to be more and more. We are getting very many, that means very less information about this in the UV visible spectroscopy. Means that if a chromophore is there, we are going to get the pi to pi star transition, and it can be measured by the Emax value. If it is more than 10,000, then we can say that the compound is having the conjugated double bond system. Okay, coming to the IR spectroscopy. In the IR spectroscopy, we are not going to take a many group like a covalently unsaturated group. We are not going to take the covalently unsaturated group. We have double bond, single bond, double bond. It is a big group, but here we are going to take only 2 atoms. So the between these 2 atoms, we should have a dipole. What is this dipole? Simply we can say that, suppose if you take a carbon carbon, the dipole is going to be 0, because the electronegativity between carbon and carbon, it is going to be 0, and this type of compounds will not give the IR spectrum. As we discussed before, if a compound have to absorb the electromagnetic radiation, the compound should have some structural requirement. If a UV visible radiation has to be absorbed, then the compound should have a conjugated double bond system. If a compound have to absorb the IR radiation, the compound should have a dipole moment or dipole. This okay. Suppose, for example, if it is a chlorine, it is IR inactive. It is not going to give any IR spectrum or IR band. Suppose if the chlorine is attached with a hydrogen, then the electronegativity is going to be different for a chlorine and different for a hydrogen. It is going to be IR active. Likewise, if you take carbon and carbon, it may be IR inactive. If a carbon is attached to hydrogen, it will be IR active. If a carbon is attached with oxygen, it is IR active. If a carbon is attached with a nitrogen, then it is IR active. So when the electronegativity is going to be different between 2 atoms, the IR spectrum, that means it is going to be IR active, and we are going to get the IR spectrum. Very simple. Okay, when the compound is absorbing the IR radiation, we all know that it will undergo different types of vibrations. Either it may be a symmetry, that means stretching vibration, or sometimes it is a bending vibration, out of which we are going to get the IR spectrum. All this radiation put together, we are going to get the IR spectrum. So what is the range? What is the range of IR? So we can divide the IR into 3 different range: near, middle, and far IR. We are going to be more, that means concerned about the middle IR region. The middle IR is 200 to 4000 centimeter inverse. Why it is centimeter inverse? Because it is a wave number. And one more thing I'll say, that each and every spectroscopical technique, we will get a peak. But only in the IR we are getting a dips. It is called as a dip. Because it is not a peak, it is a dip. Because the y-axis is going to be transmittance. When the transmittance is 100%, there is no absorption. When it is started absorbing, the transmittance will reduce, and it will be very less, and again it go and it will give the dips. Okay, so what we are concerned about the middle IR region. It is 200 to 4000 centimeter inverse. In general, we can say it is between 400 to 4000. centimeter inverse is the range, middle IR region. So this is going to give much information about the molecule. Generally, the IR spectroscopy, we would have studied that it is used for the functional group identification. Functional group identification. So it is like it is a fingerprint technique. It is a fingerprint technique. So why it is called as a fingerprint technique? Because no two compounds will not have the same IR spectrum. How no two person will not have the same fingerprint? Like no two compounds will not have the same fingerprint region. So what is the range? We can start from 400 and it goes up to 4,000. So we can divide this range into different zone. The first zone is that it is more important. It is 400 to 1500 or 1600 up to 1600. It is called as a fingerprint region. So in the fingerprint region, no two compound will not have the same IR spectrum. So here we will get all, that means mostly we will get a bending vibration, or sometimes we may get the stretching vibration also. So apart, next range is the double bond region. Next range is the double bond region. It is from 1500 to 1900 or 2000. It is called as a double bond region. If a compound have C double bond O or C double bond N or C double bond C, then we are going to get a band in this region. So what it indicates, if in IR spectrum, if you get a band here between 1500 to 1900, then you can say that the compound is having double bond. The compound is having double bond. Then from 2000 to 2400 or 500, it is called as a triple bond region. The triple bond region, if a compound is having C triple bond N, or sometimes if the compound is having C triple bond C, and if you get a band here, it means that the compound is having 100%, the compound is having a C. That means it is a triple bond. It is a triple bond the compound is having. Then comes the hydrogen region, or otherwise we can say it is a single bond region. So it is a highest energy region. In this we are going to get CH, OH and NH. All these three we are going to start from 2800, start from 2800 and it goes up to 3600 or 3700 up to that. So we can say that this is the single bond region. So what is in the IR spectroscopy? The IR spectroscopy, the compound, or there should be a dipole between two atoms. That means the electronegativity should be different between two atoms. Only those two atoms, that means those atoms will give the IR spectrum or the IR active. When the applied IR frequency is equal to the natural frequency of vibration, we are going to get the IR spectrum. And we are going to see in the middle IR region between 400 to 4000 centimeter inverse. In the middle IR region, again, we can divide into four main zone. The first one is the fingerprint region. It is between 400 to 1500. Here, no two compounds will not have the same IR spectrum, whereas this is called as a functional group region. The functional group region ranges from 1500 to 4000. 1500 to 4000. So it is called as a functional group region. Why it is called as a functional group region? In this region only, we are going to get all the functional groups. Either if it is between 1500 to 1900, it is a double bond region in which we are going to get C double bond O, C double bond N and C double bond C. And if it is a triple bond region between 2000 to 2400, it is a C triple bond N sometimes, or it is a C triple bond C. After that, from 2800 to 4000, we can say it is a single bond region or a hydrogen region in which we are going to get the CH, then NH, then OH. Okay. Now, we know that if a compound, if it is having the double bond or triple bond, it is going to give the IR spectrum in the range of double bond region or in the triple bond region. Now the question arises, how to identify whether the compound is having the double bond or triple bond or a cyclic structure. So for that, we need to understand the index of hydrogen deficiency. So what is this index of hydrogen deficiency? The index of hydrogen deficiency is a count of how many hydrogen molecule is needed or to be added to a structure in order to obtain the corresponding saturated acyclic species. What it means? Suppose, for example, if you have C double bond C, if you want to saturate this C double bond C, that means if you want to saturate this pi bond, you need to add two hydrogens here, once this side and this side. So this will become a normal alkane. If we add one molecule of hydrogen, one pi bond is going to be saturated. One pi bond is going to be saturated. So the index of hydrogen deficiency is a count of how many molecules of hydrogen need to be added to a structure in order to obtain the corresponding saturated acyclic species. Suppose, for example, if it is a C triple bond C. Now in this case, we add two hydrogen here to saturate this pi bond and two hydrogens here to saturate the another pi bond. So it need two molecules of hydrogen, or otherwise we get four hydrogens are required to saturate this triple bond. Here we need two hydrogen to saturate this double bond, four hydrogen for a triple bond. And when we divide this number by 2, we are going to get some number. Here we are going to get 2, here we are going to get 1. So now the index of hydrogen deficiency says that if the index of hydrogen deficiency is 1, so what it means, the compound may have a double bond. The compound may have a double bond. If the index of hydrogen deficiency is 2, then we can say that the compound may have a triple bond. Or sometimes the compound may have a two double bonds. You can see it here. Suppose here you can say it is a CH3, it is a saturated compound, it is a ethane. When we add a pi bond, there is a reduction in two hydrogen. So what it means that when there is a two hydrogen less, there is a formation of one pi bond. Here you can see when it is becoming a triple bond, the hydrogen here it is 6, here it is 2. It means there are 4 hydrogens are less and it is involved in making up a 2 pi bonds. And this side you can see there is no double bond. Here one double bond, there is a reduction in 2 hydrogen. Here we have a 2 double bonds, there is a reduction in 4 hydrogen. So in this case, there are 4 hydrogens are less. Here also there is 4 hydrogens are less. If you divide by 2, here also you will get the index of hydrogen deficiency is 2. Here also the index of hydrogen deficiency is 2. So what it means, if the index of deficiency is 2, it means that the compound may have one triple bond, or sometimes the compound may have two double bonds. I repeat, what is the index of deficiency? We need to calculate how many hydrogens are required to saturate the compound. And if you add, if you can find out how many hydrogens are required, that will be divided by 2, and you are going to get a number. If the number will tell you whether the compound is having the double bond or triple bond. Okay. Suppose if one more thing is that if you see a cyclic structure, so it is a simple cyclic structure. It is not aromatic structure, it is a cyclic structure. So to saturate or to open this ring, how many hydrogens are required? We need 2 hydrogens are required to open up this ring. So in this case also, the index of hydrogen deficiency will be 1. So if it is a double bond, the index of hydrogen deficiency is 1. If it is a cyclic structure, then also the index hydrogen deficiency is 1. So whenever you are getting the index hydrogen deficiency is 1, so what you will do, directly you will go to the IR spectrum and you will see between 1500 to 1900. And in the 1500 to 1900, if you get a band, then you say the IHD, that means index hydrogen deficiency is 1, and the IR spectrum shows one band here, then you can say that the compound is having one double bond. This double bond may be either C double bond O or C double bond N or C double bond C. That we will see later. What is index site deficiency? It will say about whether the compound is having unsaturation or not. That how many unsaturation, or how many double bonds or how many triple bonds. Suppose if the index of deficiency is 1, if the index of deficiency is 1 and the IR spectrum doesn't show any type of band between 1500 to 1900, it is a flat. So what it indicates that the compound doesn't have the double bond, but it has the cyclic structure. It has the cyclic structure. So index of deficiency is 1, then the compound may have either double bond or maybe a cyclic structure. Okay. If the index of deficiency is 2, so what we discuss, suppose if the index of deficiency is 2, so what we need to do? Immediately we should see the IR spectrum between 2000 to 2400 range. And if you get a band here, then you can say that the compound is having triple bond. The compound is having triple bond. Okay, if it is not there, the index of deficiency is 2, but though there is no band between 2000 to 2400, then you should see the double bond. If you get two peaks here, if you get two bands here, so it means that index of deficiency is 2, and in the triple bond region there is no band, whereas the double bond region we are getting two bands. It means that the compound is having two double bonds. The compound is having two double bonds. The compound doesn't have the triple bond. Okay, index of deficiency is 2, but in this range you are getting only 1. In the double bond region you are getting only 1. So what it indicates? The compound is having one double bond and one cycle. One cycle, because the index of deficiency is 2. Whereas we don't have any band in the triple bond region, we have only one band in the double bond region. So one band for double bond and one is for the cycle. So what do you mean by index of deficiency? It will tell about the unsaturation. If the index of deficiency is 1, the compound may have one double bond or maybe a cycle. If the index of deficiency is 2, the compound may have one triple bond or sometimes two double bonds or sometimes one double bond, one cycle. And one more example, I'll say that if the index of deficiency is 2 and the compound doesn't have any band between 1500 to this 2400, but what it says that there is no double bond, there is no triple bond, whereas it has two cycle. There will be a two cycle here. So that is what the information we get out of this index of hydrogen deficiency. Suppose if you have an aromatic ring, benzene, how many hydrogens are required to saturate this benzene ring? To saturate this double bond, we need two hydrogens. If we want to saturate this, we need two more hydrogen. If we saturate this, we need two more hydrogen. So total 6, but not at over. We need to open this ring also. We need two more hydrogen. Totally, we need 8 hydrogen to saturate the benzene ring. So 8 divided by 2, you will get 4. Whenever the index of deficiency is 4 or more, then you may say that the compound might have the aromatic structure, So what information we get? If it is 1, the compound may have one double bond or one cycle. If it is 2, the compound may have two double bonds, or sometimes one triple bond, or sometimes one double bond, one cycle, or sometimes two cycles. If the index of deficiency is 4 or more, then you can say that the compound is having the aromatic ring. The compound is having the, maybe the compound is having the aromatic ring. So what is IR spectrum and how to see the IR spectrum? If the dipole moment is there, the compound will be IR active and it is going to give the IR spectrum. And we have a different range here, the fingerprint region, then the double bond region, then the triple bond region, then comes the single bond region or the hydrogen region. And if the index of deficiency will say about how many hydrogens are required to saturate that compound having the same number of carbon atom, and if the index of deficiency 1 or 2 or 3, then we can say, and we can go and check the IR spectrum and say that whether the compound is having the double bond or triple bond or a cycle, okay. Now how to identify, that means the index of hydrogen deficiency. We need to calculate the index of deficiency. We know that if the index of deficiency is 1, then you can say it is a double bond or a cycle. How to calculate it? For that, there is a rule of 13. What is this rule of 13 says that we can calculate the expected base formula having the carbon and hydrogen. Why it is 13? Excuse me. The mass of carbon is 12. For hydrogen, it is 1. If you add these two, you are getting 13. So that is why the name has given, it is given that it is rule of 13. Very simple. When you get the molecular weight, when you know the molecular weight, see, have you ever thought that if anyone say one number, suppose if I am saying 66, can you able to write the molecular formula? That means the base formula, the compound having the molecular weight of 66, how many carbon and how many hydrogens we can write. So for that, what we need to do, we need to divide the molecular weight by 13. We need to, here m is the molecular weight, we need to divide the molecular weight by the 13. So when we divide by 13, suppose anything is divided by 13, suppose you take 27 for our simple example, divide by 13. What you are going to get? 2 13s are 26. 2 13s are 26. 1 is the remainder and divided by 13. It will become a mixed fraction. So that is what here it is written. N is the numerator, R is the remainder, and 13. Whatever the molecular weight, whether it is a 170, you divide by 13. So you are going to get some numerator, some remainder, some, that means it is 13. It is a mixed fraction. So what is the general molecular formula? The molecular formula will be CnHn plus R. Number of numerator is equal to number of carbon. Number of numerator, that means whatever the numerator comes. In this case, if it is a 2, so the compound which is having the molecular weight of 27, it has 2 carbon. How many number of hydrogen? N plus R. In this case, we have numerator is 2, remainder is 1. The hydrogen is going to be 3. So this is the base formula. This is the base formula to calculate the molecular formula for any compound, that means any molecular weight. So I repeat, we divide by 13. We are going to get the numerator and remainder. how much is the numerator, that is equal to the number of carbon, how much is the remainder that will be added to the numerator to get the number of hydrogen. Now we calculate the index of hydrogen deficiency with the formula U is equal to numerator minus remainder plus 2 by 2. What is in this case? In this case, numerator is 2, remainder is 1 plus 2 plus 2 by 2. What is the value? 4 minus 1, that is equal to 3 by 2, it is equal to 1.5. It is equal to 1.5. Remember that the index of hydrogen deficiency can be a whole number. That means either it may be 0 or it may be 1, it may be 2, it may be 3, it may be 4, it may be 5. But it cannot be in the minus 1, minus 2, minus 3 will never come. If it is coming, there is something wrong in the calculation, and you will not get in the fraction. You will not get in the fraction. And if you get in the fraction, I will tell you directly, you can say, because here also we have a trick. Suppose if you have a 1.5, 2.5, 3.5, then it is not possible. You'll have to convert into a whole number. You need to convert into a whole number, that we will see how to convert it or how to calculate the actual index of hydrogen deficiency. This index of hydrogen deficiency, there is a condition that the compound is made up of only carbon and hydrogen. But all the cases, it will not be a carbon hydrogen. Sometimes there may be oxygen. Sometimes there may be a chlorine. Sometimes there may be a nitrogen in the compound. So in that case, the index of hydrogen deficiency will be changed and the molecular formula also will be changed. How it is going to be changed? For example, if the molecular weight is 66, for example, we'll take 66. That is divided by 13. How much you will get? 5 13s are 65. Remainder is 1 and 13. What is the general formula? It is C5H5 plus 1. That is equal to 6. So C5H6 is the general molecular formula. Well, if the compound is having only carbon and hydrogen. Suppose we think we get the information from the IR spectrum that or anything in the NMR or anywhere the compound is having oxygen. So what you should do? You should add a oxygen. But directly you cannot add oxygen here. If you add oxygen, what will happen? The molecular weight is going to be changed because it is going to be 66 plus 16. But the molecular weight cannot be changed. You should add oxygen. Then what you should do? You should minus or subtract 1 carbon, 4 hydrogen. This is 16. It is equal to the mass of oxygen. It is the equal to the mass of oxygen. What is the mass of oxygen? It is 16. We are going to subtract from the C5H6 CH4 and we can add 1 oxygen. So what is the molecular formula will become? It will become C4H2 and 1 oxygen you can add. Are you getting? I repeat, 66 divided by 13, you are getting 5, 1 plus 1 by 13. The general formula will become C5H6. We forget about this. And in the IR spectrum or NMR spectrum, we are getting the evidence that the compound is having oxygen. What is the evidence? How we are going to see that we will discuss. Okay. We are getting the evidence that the compound is having oxygen. Now we need to add oxygen. When we are going to add oxygen, the molecular weight cannot be changed. So we need to subtract equal to the mass of oxygen. Mass of oxygen is 16. We are subtracting CH4 and we can add oxygen, the molecular formula will become C4H2 and oxygen. When we add oxygen, the index of deficiency also will change. What is the index of deficiency? First, the N is 5, remainder is 6 plus 2 by 2. Okay. Yes, it is clear. 5 13 sir 65, 5 plus 1 by 13. Okay. So 5 minus 6 is the what is the remainder? Remainder is a 1, not a 6. Remainder is a 1. Sorry. 5 minus 1 plus 2 by 2. So what is the value? It is 5 plus 2 is equal to 7. 7 minus 1 is equal to 6 by 2. The index of deficiency is becoming 3. When if the compound is having only carbon and hydrogen, but here we added oxygen. So what will happen? Index of deficiency, index of hydrogen deficiency also will change. So how it will change? 3 plus 1 is equal to 4. For every oxygen added, this is the table. Suppose if you want to add oxygen, you can add oxygen. You need to subtract the equal amount of carbon and hydrogen. You need to add plus 1 to the index of hydrogen deficiency. Before the index of deficiency is 3, you added 1 oxygen, then it will become 4. Suppose you added 2 oxygen. So what it will become? You add 2. So 3 plus 2, it will become, the index of deficiency will become 5. Likewise, if you want to add a nitrogen, you can add a nitrogen. How much? That means what you need to subtract? You need to subtract CH2, carbon for 12 and hydrogen, 2 hydrogen for 2, so total 14. What the index of deficiency will become? Half. I have given before, just 5 minutes before, I told that the index of deficiency will be 0, 1, 2, 3, 4, like that. It will be a whole number. Whenever you are getting a fraction, suppose 1.5, 2.5, 3.5, what it indicates, the compound is having nitrogen. The compound is having nitrogen. It is sure, because the nitrogen rule, we will see in the mass spectrum, spectroscopy, whenever we discuss. What is nitrogen rule says that if the molecular weight is odd, suppose whenever there is a molecular weight, if a molecular weight is odd number, whenever it is 65 or 77 or 109, whenever you are getting the odd number of molecular weight, what the nitrogen rule says that the compound is having the odd number of nitrogen. The compound, there is 100% nitrogen is present, that is also in the odd number, either 1 nitrogen or maybe 3 nitrogen or maybe 5 nitrogen. So whenever you divide this 65, 77, 109, any odd number, you are going to get a fraction. It will be 1.5, 2.5, 3.5. So whenever there is a fraction, you can add a nitrogen and you can subtract CH2 and you can add plus half, then the 1.5 will become 2. 1.5 will become 2, then you can see the IR spectrum, then we can come to the conclusion. We can come to the conclusion. So is that clear? What is index hydrogen deficiency say? Index hydrogen deficiency say that how many hydrogens are required to saturate a particular compound. If the index hydrogen deficiency is 1, the compound may have 1 double bond or 1 cycle. If the index hydrogen deficiency is 2, the compound may have a 1 triple bond or sometimes 2 double bonds or sometimes 1 double bond, 1 cycle or sometimes 2 cycle, 2 cycle. So this is how we can get the information in the index of hydrogen deficiency. How to calculate it? How to calculate it? For that we have rule 13. The rule 13, we think that first the compound, any compound is made up of only carbon and hydrogen. So that is why we are going to divide the molecular weight by 13. From where we are going to get the molecular weight? The molecular weight we are going to get from the mass spectrum. We are going to get from the mass spectrum. So whatever the mass spectrum, we are getting the molecular weight that will be divided by 13. You are going to get some numerator and remainder. You can or you can generate a general formula. By keeping the general formula, you can calculate the index of hydrogen deficiency. It may come 0, it may come 1, or it may come 2, or it may come 1.5. So if you get the information from IR or NMR that oxygen is present or nitrogen is present or chlorine is present or bromine is present, then you can add either chlorine or bromine or nitrogen or oxygen, but you'll have to subtract equal amount of carbon and hydrogen. Suppose, for example, if the compound is having bromine, so you need to subtract C6H7 equal to 79, and you need to -3. You need to go for -3 in the index of hydrogen deficiency. Okay. Now I'll come to higher spectrum once again. How to identify whether the compound is having oxygen or nitrogen or anything. We told that this is the double bond region. The double bond region ranges from 1500 to 1900. The C double bond O, we are going to get a peak or a band around 1700. Around 1700. Either it may be 1720 or 1715 or it may be 1680. We can say for our convenience it is a 1700. If it is around 1700, you are getting any band, then it is the presence of C double bond O. Okay. So C double bond O is present. So when you say that C double bond O is present in a molecule, what are all the possibilities? What are all the possibilities? Sometimes, if it is present as a C double bond O and hydrogen, then it is a aldehyde. It is a aldehyde. Sometimes C double bond O and any one alkyl group, then it will be a ketone. Or sometimes we may have a OH, then it will be a carboxylic acid. Sometimes we may have NH2. Sometimes we may have NH2, C double bond O, NH2. Then it will become a amide. It will become amide. Or sometimes we may have a OCH3. Then it will become a ester. Then it will become a ester. So these are all the options. These are all the options. Suppose if you get a band around 1700, then we need to check whether it is an aldehyde, whether it is a ketone, whether it is a carboxylic acid, whether it is a NH, whether it is a amide, whether it is a ester. So how to check this? Suppose if it is a carboxylic acid. So we have 1700 C double bond O, and directly you come to the single bond region here around 3600 around. If you get a band for a OH, then you can say that the compound may have a carboxylic acid. That means OH also is present and C double bond O also is present. Then you say it is a carboxylic acid. Okay. And C double bond O is present. There is no OH. There is no OH. So like that, it is a complementary. So there is no that means hard and fast that only it will be like that only. But how to read, I'm just want to say that suppose if it is a amide, first you will see that C double bond O around 1700, then you will check for the NH2. You will check for the NH2. Where you will check for the NH2? NH2 will come around 3400 or 500. You will get two band like this. So it is for the NH2. So you have 1700 C double bond O and you have NH2, then it is a amide. Then it is a amide. So if the index of deficiency is 1, we will see the double bond region. And in the double bond region, if you get 1700, then it is a C double bond O. And around 1620, around 1600, if you get a band, then it is a C double bond C. C double bond C. The same range you will get a C double bond N also, But how to differentiate C double bond C and C double bond N? We discussed that molecular weight. If the molecular weight is odd, then you may think that the compound may have a nitrogen. The compound may have a nitrogen. So simple. If it is 1700, it is C double bond O. If it is 1600, it is C double bond C. Likewise, 2200, if you get a band, then it is a C triple bond C. And here we can say that it is going to come CH, then NH, then OH. So how to differentiate this? How to differentiate this? The key is 3000. The key is 3000 centimeter inverse. 3000 centimeter inverse. If the CH group is sp3 hybridized, if the CH is sp3 hybridized, we are going to get less than 3000. That means if a compound is having CH3, CH2, anything is only single bond, then the CH stretching we are going to get less than 3000. It may be 2950 or it may be 2980, but it will not cross 3000. It will not cross 3000. Okay. If there is a sp2 hybridized hydrogen, then C double bond C, if it is hydrogen, if it is a CH stretching in the double bond, then where it will come? I told that 3000 is the key. Less than 3000 is the sp3. More than 3000, more than 3000, if more than 3000, less than 3100. Less than 3100, if you get a band, then it is a sp2 hybridized CH stretching. And 3300, it is a sp hybridized CH stretching. If it is a sp hybridized, then it is going to get around 3300. So I repeat, 1700 C double bond O, 1600 is C double bond C, 2200 is C triple bond C, less than 3000 it is a sp3 hybridized CH, more than 3000, less than 3100 is the sp2 hybridized CH, 3300 is the sp hybridized CH, and after that we get NH, then we get a OH, then we get a OH. This is the range how we are going to read the IR spectrum. How we are going to read the IR spectrum. Clear? Hello, sir. Prashant, sir. Okay. So index added deficiency and the rule of 13 we discussed. So here we have the simple model IR spectrum. As I told that in this double bond region, either it may be C double bond O, C double bond C, C double bond N. In this triple bond region, the C triple bond N or C triple bond C. Here comes the CH less than 3000, and here comes the NH and OH around 3500 or 3400 range. There will be a NH and then OH. So coming to the NMR spectroscopy, what information that we are going to get from the NMR spectrum? So as we told that we discussed in the electromagnetic radiation, if a compound have to absorb the UV radiation, the compound should have a chromophore. Then if a compound have to be IR active, then it should have a dipole moment between two atoms. Here in the nuclear magnetic resonance spectroscopy, we are going to study the compound at the level of a nucleus. At the level of a nucleus, that means we are going to study about the individual atom. Individual atom. Suppose if the compound have to be NMR active, that means how we are going to study. I'm not going to go for the that means principle. If you want to study about the hydrogen, then we are going to go for the proton NMR. If you want to study about the carbon, we are going to go for the C13 NMR. Like that, phosphorus, we are going to 31, and silicon, like that, platinum, we can use any type of NMR. Mostly we use proton NMR and C13 NMR. So again I'm saying in the UV we get a chromophore, it is a group of atom. In the IR we get only two atoms, whereas in the NMR we are going very fine and we are going to read about individual atom at the level of a, that means at the nucleus level we are going to study about the individual atom. So how we are going to read, how we are going to read the NMR spectrum. So in the NMR, proton NMR, we are going to talk about the proton NMR. In the proton NMR, we are going to talk about the shielding and deshielding. What is shielding and deshielding? If here there is a proton, here also we have a proton. This proton is said to be shielded proton. This proton is said to be less shielded or deshielded. Why? Because this proton is directly attached with the oxygen. The oxygen electronegativity is high. It will that means attract all the oxygen, sorry, electron towards this oxygen. This hydrogen will be less of electron crowd. When the electron crowd is less near to any hydrogen, then that hydrogen is said to be deshielded. So like this, if we take this hydrogen, it is attached with the carbon. The electronegativity of carbon is more than hydrogen, but it is less than oxygen. It is less than oxygen. So when compared with this proton is said to be more shielded, more shielded. So depending on the environment, chemical environment, the protons in the molecules are shielded or deshielded. So based on this, there will be a chemical shift. So now what do you mean by chemical shift? Chemical shift is nothing but the shift of an NMR signal from the signal of TMS. From the signal of TMS. What is this TMS? TMS is the tetramethylsilane. Tetramethylsilane is the standard. It is the reference compound that we use in the NMR spectrum. The TMS will be kept in the zero. That means if you take a delta, it is called as a delta scale. The delta scale, that means it is ranges from 0 to 10 most of the time. Sometimes it goes up to 12. Sometimes it goes up to 12. We are going to keep the TMS tetramethylsilane at 0. From the TMS, where you are going to get your NMR peak will tell about the chemical shift. That means the relative position of your proton from the TMS is the chemical shift value. How to calculate? Shift in frequency from the TMS in hertz. Frequency of spectrophotometer. Frequency of spectrophotometer will give you some delta value. So the delta value we are going to get. What information we are going to get from the NMR? NMR, what information we are going to get? We are going to get four main, that means important information about the proton. First one, the number of signals will say about how many different types of protons are there or hydrogens are there. Number of signal. Suppose if there is 3 signals, then you say that there are 3 different types of protons are there in a molecule. If there is only one signal, it means that all the proton present in the compound, it is all are in the same environment, or we can say that we can say equal and non-equal. So what do you mean by equal and what do you mean by non-equal? For example, if you take CH3 and CH3, it is a simple ethane. Simple ethane. In this, how many hydrogens are there? How many protons are there? There are 6 protons are there. 6 protons are there. If you replace any one proton, suppose here it will become 2. Here you add chlorine. What is this compound? It is a chloroethane or 1-chloroethane. Because all the protons, suppose if you replace here, then also it will become a 1-chloroethane. Means suppose if you could not able to understand which proton is equal, which proton is non-equal, What you can do, you can replace one hydrogen with any one group, and you can name the compound, and you can easily understand whether it is equal or non-equal. Suppose, for example, it is CH3, CH2, CH3. Here we have 3 carbon, and totally there are 8 protons. There are 8 protons. 3, 2, 3. In this, here, if you replace any one proton and replace with the chlorine, it will become a 1 chloropropane. 1 chloropropane. Same time, suppose it is a, it is B, and it is C. The C carbon, one hydrogen is replaced, you are getting 1 chloropropane. Same way, in the A carbon, one hydrogen if you replace CH2, CH2, CH3. So what this compound? This also 1 chloropropane. It means that these 3 protons and these 3 protons are equal. Because when you replace any one proton, you are going to get an identical structure or identical product. If you are getting the identical or the similar product, you can say these 6 protons are similar. Suppose in the B carbon, if you replace any one hydrogen and add chlorine, it will become 2 chloropropane. It will not become 1 chloropropane, it will become 2 chloropropane. That means that these 2 protons are different from this 6 proton. These 6 protons are equal, these 2 protons are different from this 6 protons. Okay, I will say in another way, these 6 protons are equal, these 2 protons are equal, whereas these 2 protons are non-equal to this 6 proton, and these 6 protons are non-equal to these 2 protons. So number of signal will say how many different types of protons are there in a molecule. Suppose, as I told, if you get 3 signals, it means there are 3 different environment is there in a molecule, or otherwise in other word we can say there are 3 different types of protons are there in a molecule. That is the point number 1. What is point number 2? Position of the signal will say which type of proton or which type of hydrogen is this. What is position of signal? As we told that there is a delta scale. There is a delta scale. At 0 position, we have a TMS. 0 position, we have a TMS. From the TMS, where you are going to get your signal, that will say which type of proton is this. For example, this is the delta scale. And if you see, you can divide how we divide the IR range, like fingerprint region and the functional group region. Again, we divided into different double bond, triple bond, hydrogen region. Like that, here also we have different region. For our convenience, we can just draw a line here. And from 0 to 1.5, 1.8, you can see here it is a CH. Whether it is a primary, secondary, tertiary proton, then it is going to give a signal here. The next range it is going to, that means here we can draw a line for it is C. Once again, it is for our understanding only, because it is from 1, 2 to 4, you can say you have many type of proton. For example, it is a sp3 hybridized proton, and this proton is nearby the C double bond O, like that OH, NH proton, and this is the benzyl proton, aromatic ring, then CH. This is the benzyl proton. And what is this proton? C double bond C, then CH. It is a allyl proton, because there is a difference. This is the allyl proton and this is the vinyl proton. Vinyl proton will come 4 to 6, whereas allyl proton will come 2 to 4. So the position of the NMR signal, what is the number of signal will say number of different types of proton. Second point will say that the position of the signal will say which type of proton, whether it is a primary, secondary, tertiary proton, or whether it is a allyl proton, whether it is a hydroxyl proton, whether it is a ns2, whether it is a anything, that is the position will say. The next range is 4 to 7. The 4 to 7 you get phenol, phenolic OH, this OH and allylic hydrogen, sorry, vinyl hydrogen. This vinyl hydrogen and phenolic hydrogen will come in this range. Then 7 to 9 you can see there is a aromatic proton, there is a aromatic proton. From uh, 10, above 10 you are going to get two proton. This is aldehydic proton and this is carboxylic proton, this is carboxylic proton. So you get a delta scale. If any signal you are getting more than 10, then what you will say, the proton either it may be aldehyde or it may be a carboxylic acid. If any signal you are getting between 7 to 9, suppose you are getting any signal, what it indicates, the compound is having the aromatic proton. Any signal you are getting between 4 to 7, then you can say it may be a vinyl proton or it may be a phenolic proton. Any signal you are getting here, we have so many options between 2 to 4. Either it may be a OH, it may be a NH, it may be allyl proton, or it may be a sp hybridized proton. Any proton you are going to get the signal here. So what the second point, the position of the signal will say which type of proton is this, which type of proton is this. The third point will say what is the relative area or relative position or relative peak intensity. Suppose for example we have one signal, very high signal, one is like this, one is like this. That means here is the intensity is less, here it is little more, and here we have little more. What is this relative area say? Suppose here you will be having the integration in the NMR spectrum, it shows that 1.0. What it say that there is one proton is involved in this particular signal. Suppose here we can say it is 1.9. So what it says that there is two protons involved in this particular signal. Here it will be 3.1 or 3.0. So it is saying that there is three protons involved in it. So the number of signal will say, now in this case there are three different types of environment, and that is why we are getting three signal. But each signal, in this signal there is two protons are involved. In this signal there is only one proton is involved, whereas here there is three protons are involved. That is what it indicates, that the relative in areas or the peak intensity will say how many hydrogens are of each type, how many hydrogens are involved in a particular signal. See it here. Here it shows 2.96. It means that there are three proton. It is a single signal. It is a single signal. We will see the next point how it is getting splitted. First we'll understand 2.96. It means that there are three protons are involved. Here you can see 3.04. There are three protons are involved in this signal. Here you get 1.99. There are two protons are involved in this particular signal. So first thing is that there are three signal. There are three different protons or three different types of protons are involved. Now the position will say which type of proton is this. Third, the integration will say how many protons are involved. So for example, in this case, totally there are 8 protons are there in a molecule. 3 is here, 3 is here, and 2 is here. So totally there are 8 protons are involved in this particular signal. So number of signal will say how many environment, position will say which type of proton, the relative intensity will say how many protons are involved in the particular signal. The last one, the splitting pattern, how the one signal is going to be splitted. Here we have seen that this is one signal, but it is splitted into three. But here it is a one signal, it is not splitted at all, it is a splitted at all. Here one signal, it is showing us a four signal, it is splitted. How it is going to be splitted? So for that we have a splitting pattern. It is a n plus 1 rule. N plus 1 rule. What is n plus 1 rule? How many number of non-equivalent adjacent proton? What is n indicates how many number of adjacent non-equivalent proton. Suppose for example, as the same example will take CH3, CH2 and CH3. As we discussed earlier, this three proton and this three proton, that means total 6 protons are in the same environment, or we can say they are equal. And these two protons are equal, but these two protons are non-equal to these 6 protons. And these 6 protons are non-equal to these 2 protons. So what is n? Number of protons on an adjacent carbon atom which is non-equal to that particular carbon atom, that means that proton. So what is n? N is the number of protons in the adjacent carbon atom. What is n plus 1? Number of adjacent proton plus 1. Suppose if n is equal to 1, that means suppose we have 2 carbon, here we have 1 hydrogen, here we have 2 hydrogen, here we have 2 hydrogen. So adjacent, how many hydrogens are there? 1. So how this signal is going to be splitted? N plus 1 is equal to 2. So it is called as a doublet. So that means one signal is going to split it into equal intensity. What is 1:1 indicates that this signal is going to be splitted. Both will have a equal intensity. Suppose here we have 2 protons. How it is going to be splitted? This signal is going to split it into 3. When it is going to split it into 3, the intensity will be 1 is to 2 is to 1. You can see it here. How it is going to split it? It is split it into 3. It is 1 is to 2 is to 1. If one signal is split into 3, it is going to be 1 is to 2 is to 1. So how it is going to split it? 1. Suppose one signal, it is going to split it into 2. It is 1 is to 1. It is almost equal. Then if it is split into 3, 1 plus 1 is equal to 2 and 1. That means 1 is to 2 is to 1 is the ratio. Suppose one signal is split into 4. Then how? 1 plus 2 is equal to 3. 2 plus 1 is equal to 3. Then 1. You can see it here, it is a quadrat. So 1 is to 3 is to 3 is to 1. Suppose if it is split into 5. So how it is going to split it? 1 plus 3 is equal to 4. 3 plus 3 is equal to 6. 3 plus 1 is equal to 4 and 1. If one signal is going to split it into 5, then it will be 1 is to 4 is to 6 into 4 is to 1. So like that, how the splitting will happen? If there is one non-equivalent proton, adjacent proton, it will be a doublet. If it is 2 non-equivalent proton, it will be a triplet. If it is a 3 non-equivalent proton, it is going to be the quadrat. And if it is 4, it is going to be the quintet. And if it is 5, it is going to be the sextet. And if it is 6, it is going to be the septet. And after that, we say it is a multiplet. It is a multiplet. We cannot go for heptet, octet, nonet like that. We don't go. We say it is a multiplet. So, what information we are going to get from the NMR signal? NMR signal will say 4 information. One is that the number of signal will say how many different types of proton. The position will say which type of proton. The relative area, that means the intensity, will say how many protons are involved in that particular signal. The splitting pattern will say how many non-equivalent neighboring protons are present in that compound. How many neighboring non-equivalent protons. So, suppose if it is splitted into if it is splitted into 3, what it indicates if it is splitted into 3? How many non-equivalent protons are there? There are 2 non-equivalent protons are there. It is not at all splitted. It is not at all splitted. What it indicates, there is no neighboring proton because it is a singlet. There is no neighboring non-equivalent proton. Neighboring non-equivalent proton. It is splitted into 4. It indicates that there are 3 non-equivalent protons. There are 3 neighboring protons are there. So the splitting pattern will say how much or how many protons are nearby. Why it is not getting splitted? Why it is not getting splitted? The splitting will happen only in general case in the 3-bond coupling. The 3-bond coupling. What is 3-bond coupling? Suppose if there are 2 carbon and this hydrogen, these 2 hydrogens are separated by 3 bonds. This is bond number 1. This is bond number 2 and this is bond number 3. So these 2 hydrogens are separated by 3 bonds. So these 2 hydrogens may be splitting each other. Suppose for example, if you take like this C double bond O carbon, and here in this case it will not get split, and here we have one hydrogen. In this case, what happened? 1, 2, 3, 4. So if this is the case, this cannot be splitted. This cannot be splitted by. So generally, what we say, it is a 3-bond coupling. Suppose here we have a CH3, this side CH2, this hydrogen and this hydrogen. How many signal? That means how many bonds are there? 1. Here we write hydrogen. Here we write C double bond O. Here we write another hydrogen. So it is splitted by more than 3 bonds. So it cannot be splitting each other. So the splitting pattern will say how many nearby non-equivalent protons are there in a molecule. So number of signal, position, relative peak, and the splitting pattern will say how many. That means information about the proton. Finally, mass spectrometry. In the mass spectrometry, when we that means in the mass spectrometrists, they don't. Hello, is it audible, sir? Hello.
Sir, you are audible, sir. Go ahead, sir.
Sir, is it okay?
Yeah, okay, sir. Please hold your mic near your mouth, sir.
Okay. Okay. The last spectrometry is the mass spectrometry. Spectroscopy is the mass spectrometry. We call it as mass spectrometry. We don't call it as mass spectroscopy. Okay. In this, what information we get? A mass spectrometrist is someone who figures out what something is by smashing it with a hammer and looking at the pieces. They are not going to. They are not interested about the whole molecule. We are going to interested about the pieces. We are going to break the molecule into different pieces, and we are going to read about that. That means by keeping the pieces, we can say that which type of compound is this. So when generally we take a molecule and it will be converted into ions, that means the ionization will happen. In the ionization, what will happen? Generally, what we do, we take a molecule and it is going to bombarded with the electrons. When it is going to bombarded with the electron, one electron will be removed and the molecule is going to be converted into positively charged radical cation. So when this process happen, this molecule is became unstable. It is unstable. So this will try to become stable. During this course, how it will become stable? It will try to fragment itself. That means it will try to leave some group and it will try to become stable. When doing this, we get one peak for the molecular weight for the compound. It is called as a M plus peak. Then there will be so many other fragments. Why these fragments? Because the molecular, that means the molecular ion is not stable and it will try to become stable. So during this process, the molecule will try to separate or leave some groups and try to will become stable. Out of all these fragment, some fragment will be highly intense fragment. Why it is highly intense fragment? We can say that this is highly stable fragment, and this highly intense peak is called as a base peak. Highly intense peak is called as a base peak, and this peak is called as a molecular ion peak. This peak is called as a molecular ion peak. So how the molecular ion peak is going to come? The emission of an electron from an electrically neutral compound leads to the production of molecular ions. So just we are going to remove one electron from the molecule. By removing one electron, we are going to get the molecular ion peak. So that is why the M plus ion will directly tell about the molecular weight of the compound. Molecular weight of the compound. And the highest intense peak is the base peak. Highest intense peak is the base peak. Sometimes molecular ion peak itself the base peak, all other peak will be lesser intense than this. What it indicates that the molecular ion itself is the highly stable cation, whereas in this case the molecular ion is not stable, whereas some other fragment is highly stable. So what information, how it is going to how we are going to read the mass spectrum? Mainly we are going to see the M plus peak. If the M plus peak we are getting, the M plus peak will say about the molecular weight of the compound, because as we discussed before, the rule 13 and the index hydrogen deficiency, we are going to start that means our practice when we that means it is going to start from the molecular weight of the compound. Okay. So nitrogen rule, I told that when the M by Z value, that means what is the M by Z? The mass by charge value. If it is even, then we say that there is a even number of nitrogen. If the M by Z value is odd, then we say it is a odd number of nitrogen. Okay. Here we can see M plus peak is 72. All other 57, 43, 29, all are fragment ion peaks, whereas 43 is P labeled as a base peak because it is the highest intense peak, and we can say that it is the relative abundance of this peak is 100%. We calculate this as 100%. By keeping this, the other peak value abundance will be calculated. So make it very simple. We are going to remove one electron from the, or we are going to ionize the molecule, and we are going to get the M plus peak. If the M plus is stable, it is going to form a highest intense peak. If the M plus is not stable, the some other peak which is stable is going to form a highest intense peak, that is called as a base peak. All other are called as a fragment ion peaks. Okay, coming to this practice. See, I request everyone to listen or take a pen and paper so we can go and we can practice, and we can try to write the chemical structure of this compound. Okay, I revise once again. If it is the UV visible spectroscopy, we are going to talk about the conjugation. If the IR spectroscopy, we are going to talk about the function group. If it is in the double bond region, either it is a C double bond O or it may be a C double bond C. If it is 1700 around, it is a C double bond O. If it is 1600 around, it is a C double bond C or it is a C double bond N. In the hydrogen region, If it is less than 3000, it is a sp3 hybridized CH. If it is more than 3000 and less than 3100, it is a sp2. It is around 3300, it is a sp hybridized CH. Then after that it comes NH, then it will become OH. In the NMR spectrum, we get four information. Number of peaks will say about the how many different types of proton. The position will say which type of proton. Then the intensity will say how many protons are involved in that particular signal. The splitting pattern will say about how many number of neighboring non-equivalent proton. The mass spectrum, we can see M plus, it is the molecular ion peak, and the highest intense peak is the base peak, and apart from the molecular ion, all are called as a fragment ion. Out of all fragment, maybe one is a base peak, remaining all are, even the base peak also a fragment ion, all are fragment ion. Okay, this is the that means spectrum, all four spectrum for a single molecule. First, we can see the UV spectrum. You can see the UV spectrum here. It is actually in the reverse form. I will show you the reference also. You can go through that. If you see the UV spectrum, here it is written 33.3 mg in 10 ml. 33.3 mg in 10 ml. What is 33.3 mg? If you calculate into microgram, 33.3 into 1000. It is 33,300. We are taken in 10 ml. That means 3,330 microgram per ml solution. 3,330 microgram per ml solution. If you take, we will be never taking this much concentration. Even though if we have taken 3,330 microgram per ml solution, the absorbance is almost 0.6 or 0.7. It means that there is no strong absorption. There is no strong absorption. When there will not be no strong absorption, we say that when there is no conjugation, there will not be no strong absorption. Simply we can say that okay. So we can say that there is no strong absorption. We can say that there is no conjugated double bond system. There is no conjugated double bond system. Okay, we'll start. Molecular weight. Molecular weight is 72. What is nitrogen rule says that there may be absence of nitrogen or even number of nitrogen because it is a even number. When it is a even number, we can say it is a absence of nitrogen or a even number of nitrogen. Next, rule 13. We are going to divide this 72 by 13. We are getting 5, 7 by 13. It means that, and we calculate the index of deficiency. U is equal to n minus r plus 2 by 2. The index of deficiency shows 0. 5 is the numerator, r is the remainder. So 5 minus 7 plus 2 by 2 will give you 0. But if you see the IR spectrum, at 1718, you can see a band. What 1718? It is clearly shows that the compound is having C double bond O. C double bond O is present. But the index of deficiency shows 0. It is not at all possible. It is not at all possible. So it is very clear that the compound is not made up of only carbon and hydrogen. The compound is having oxygen also. So what is the molecular formula? It is CnHn plus R. We add C5H5 plus 7. It will become C5H12. The general formula will become C5H12. The IR spectrum shows the peak at 1718. It is evident that there is a presence of oxygen because clearly we told that it is a C double bond O. So we need to add oxygen because the compound is not made up of only carbon and hydrogen. There is oxygen also present. So when we add oxygen, what we do? We remove CH4 from this C5H12. So from the C5H12, if we remove CH4, it will become C4H8O. C4H8O. What will be the U will become? U will become, we should add 1 because already we told that whenever we add oxygen, we should add plus 1. The index of deficiency will become 1. The molecular formula, it became C4H8O. If you see the NMR spectrum, there are three different types of protons. If you see the IR spectrum, 17, 18, we have a peak. And if you see it here, this is the CH. The CH is less than 3000. It means that there is a sp3 hybridized CH stretching, and apart from this one bond, there is no other bond. Even the triple bond also, there is no bond. So it is very clear that the compound is having one unsaturation. The unsaturation is a C double bond. In the mass spectrum, we have 72, 57, 43, and 29. Coming to the NMR, we have three peaks. The first is triplet, then singlet, then quadret. One is, it is a triplet, one the singlet, and it is a quadret. See, I will add one more thing, which will go to downfield. It is called as a downfield. It is called as a upfield. Okay. Why it is called as a downfield? Because we say that it is going away from the TMS. It is called as a downfield. If anything comes towards the TMS, it is called as a upfield. Now, which will go to downfield? Which proton or which signal will go to downfield? Which will come to upfield? If any proton is de-shielded, that will go to downfield. Any proton is shielded, it will go to upfield. When the proton will be de-shielded, if the proton is attached with any electronegative atom, then that proton is said to be a de-shielded proton. Okay. Now we have three signal. One is quadret. Quadret is highly de-shielded. Then singlet, it is less de-shielded than this quadret. Then we have a triplet. It is a shielded proton. It is a shielded proton. Okay. So keeping in this, we have C4H8O. The compound is having oxygen, and the carbon, it is having four carbon. 1, 2, 3, 4 carbon, and it is having one oxygen. The oxygen is a C double bond O. Where the C double bond O, either it may be in the second carbon or maybe in the first carbon. Yes, only two possibilities. If you keep the double bond O in this carbon, it is going to be same. And if you keep this double bond in this carbon, it is also going to be same. So only two possibilities. Either the compound may be having the double bond in the second carbon, or the compound may have the double bond in the first carbon. Suppose if you keep this, it is CHO, it will become aldehyde. It is CH2, and CH3. How it will become? It will become CH3. It is a ketone. It is CH2. It is CH3. In both the cases, it satisfies C4H8O. Here also it is a C4, 4 carbon, 8 hydrogen, 1 oxygen. Here also it is 4 carbon, 8 hydrogen, 1 oxygen. So now our compound is either of these two. Either this is our compound or this is our compound. How can we, that means conclude, or how can we confirm whether it is a ketone or it is a aldehyde? Suppose if it is a aldehyde, you can see, I will write it once again. CH3, CH2, then CH, 2, then C double bond O and hydrogen. How many different types of protons are present here? We can say this is A, B, C and D. Here we have four different types of proton. This is the aldehydic proton, and this is CH2 nearby C double bond O. This is another CH2 and another CH3. Four different types of protons are there in a molecule. Whereas here we have this is A, this is B, and this is C, and this is D. In this, we have only three different types of proton. In the B carbon, we don't have any proton. We have only three different types of protons are present here. Here we have four different types of protons. What is our NMR signal says that? NMR signal, we have only three signal. We have only three signal. So it is evident that the compound may be a ketone. The compound may be a ketone. What is the ketone? It is CH3, CH2, C double bond O. We can confirm. Again, we need to confirm. We cannot blindly, we cannot go for it. Okay. So there are three protons. There are three signals. How can we further confirm? We can say it is A, it is B, and it is C. Which proton will go to downfield? Which proton will go to downfield? A, B, or C? The B proton will go to downfield. Why it will go to downfield? Because the B proton, one side we have C double bond O, other side we have CH3. Whereas if you take a, the one side it is having C double bond O, the electronegativity for A and B differs. How it differs? One side it is C double bond O, other side we have another carbon. The electronegativity for this proton is going to be high. That is why it is highly D-shielded. We are getting B. How we are confirming B? Because nearby B there are three non-equivalent protons. There are three. What is N? N is equal to 3. So 3 plus 1, you are going to get a quadrat. We are going to get the quadrat. Second, C will not come because A will come because A is nearby C double bond O. A is coming. It is a singlet because nearby this proton there is no nearby proton because it is only carbon. Then we have a CH2. This CH2 that means this proton and this proton is separated by more than 3 bonds. So it cannot split. So we are getting a singlet. And finally, we are getting this C here. And how many nearby proton? There are 2. In this case, the N is equal to 2. So 2 plus 1, you are going to get the triplet. So first is triplet, then singlet, then quadrat. Further, we will confirm. If you see the mass spectrum, 72 minus 15. How much? 72 minus 57. 72 minus 57 will give you 15. So whenever the compound will get break, any type of ketone is going to get break, how it is going to get fragment? It is going to fragment in the alpha carbon. It is going to fragment in the alpha carbon. For example, in this case, it is going to fragment here and it is going to fragment here first. Suppose if it is fragmented here, which group will be eliminated? The CH3 is eliminated. What is the mass of CH3? Carbon 12, hydrogen 3, it is 15. So 15 is eliminated. That is why you are getting 72 minus 15, it is 57. What is the next one? 72 minus 43. 72 minus 43. How much it is coming? It is 29. It is 29. Suppose this side is eliminated. This fragment, how much it is? CH3, CH2. CH3 is 15. CH2, it is 14. So 15 plus 14 is 29. That is why you are getting M minus 29 is a 43. M minus 57, sorry, M minus 15 is 57. What is M minus 15? From the molecular ion, 15 mass is eliminated. This 15 mass is equal to CH3. M minus 40, M minus 29 is equal to 43. In this case, this 29, this ethyl group is eliminated. So that is why we are getting M minus 29. So it is confirmed that first we have taken molecular weight 72, then we divided by 13, we got a general formula. From the IR, we are confirmed that at 17, 18 we have a C double bond O. So we added one oxygen. When we added oxygen, the induction deficiency will become 1. Then we check that there may be two possibilities. From the NMR spectrum, it is confirmed that if this is the case, we should get a 4 signal, but in NMR, we are getting only 3 signals. So the compound is a 2-butanone. The compound is a 2-butanone. We take another example. So this is the IR spectrum. Here you can see there is no UV. UV absorption is no. Here we have a C double bond O. And here you can see this is the one characteristic peak for a carboxylic acid. Characteristic peak for a carboxylic acid, OH. How this OH, when the OH of carboxylic acid is present, we are going to get a broad band from 3400 or 3500 to 2500. Like this, you will get a very broad band. Suppose if it is alcohol, we don't get like this. We get one sharp peak around 3600. Additionally, C double bond O will not be there for a alcohol. If it is a carboxylic acid, we are going to get a broad band. So it indicates there is a carboxylic acid. And one more, and if you see the mass spectrum, the M plus is 74. Then 74 minus 57 is the first fragment. Sorry, okay, 74 minus 57 is the first fragment. The second one, 74 minus 45 is the another fragment. Coming to the NMR, we get one signal here, it is a triplet. We get another signal here, it is a quadret. And generally we told that the delta scale will be up to 10. Only in 2 cases the delta scale will go beyond 10. Suppose if it is a aldehyde, or if it is a carboxylic acid. If it is a carboxylic acid, you can see there is another signal more than 11. So in the IR also there is a evidence it is a OH for a carboxylic acid, and in the NMR also we have a evidence that there is a peak, or there is a peak of carboxylic hydrogen more than 10. So 100% we know that the compound is a acid. So we'll proceed further. 74, absence of nitrogen, no nitrogen, will divide by 13. The degree of unsaturation will become -1. As I told that, we discussed that there cannot be a minus. It can be either 0, or it can be 1, or it can be 2, or it can be 3. Okay. So -1. When it is a -1, we think that if the compound is made up of only carbon and hydrogen, it is -1. But we have a evidence that 17, 15 we have a peak. So we are going to add one oxygen. So the U will become 0. Why U will become 0? Because -1 plus 1. We added one proton, so it will become 0. When we added one oxygen, the +1 has to be added, it will become 0. But from the NMR, it is very clear that we have a peak around more than 10 ppm, 10 parts per million. So already we discussed that the compound is having the carboxylic group. So what we need to do? We need to add another oxygen. We need to add another oxygen. When we add another oxygen, you will remove -CH4 once again. Then your molecular formula will become C3H6O2. The index of deficiency is 1. Now it satisfies that in the IR spectrum, we have a band around 1500 to 1900. Whenever we get a band around 1500 to 1900, then there must be a U is equal to. So now we told that we came to the conclusion first, without oxygen the molecular formula is C5H14. After adding one oxygen it will become C4H10O. After adding two hydrogen it has become C3H6O2. Now the NMR is having three different types of proton. Three different types of protons. So what are the three different types of proton? The first one is a triplet. It is highly shielded. Then it is a quartet. Then we have around 11. It is a singlet. It is a carboxylic proton. Okay, now if we try to write the structure, what is the central formula? It is C3H6O2. Only three carbons. Only three carbons. Carboxylic acid cannot be in the middle, so it will be always in the terminal carbon. Always it will be terminal carbon, so it is a CH2, it is CH3. Okay, how can we confirm this? Suppose here we write the structure CH3, CH2, COOH. What is the highly de-shielded proton? It is a carboxylic proton. What is the next signal? It is a quartet. So we can say it is a A and this is B and this is C. Which will go to the downfield? This B, this proton will go to downfield. Why? Because it is near to C double bond O. What is the neighboring proton? In this case, neighboring proton N is equal to 3 because this side there is a CH3. So this signal is going to split it into 4. That is why you are getting quartet. Then comes this A. In this case, A nearby how many non-equivalent proton? There are two non-equivalent proton. That is why this signal is split into 3. It is a triplet. So this is the first confirmation. Coming here, 74 minus 57. 74 minus 57. How much? It is 17. Why it is 17? OH is eliminated. When the OH is eliminated, it is 16 plus 1. It is 17. So OH is eliminated. You are getting 74 minus 17. It is 57. Then 74 minus 45. How much it is coming? 74 minus 45. 29. So what is this value? CH3, CH2? It is 29. So M minus 29, M minus 17. So further it is confirmed that our compound is a carboxylic acid. Our compound is a carboxylic acid and that is the structure for this compound. Okay. Sir, shall I go for the third one? Prashant, sir.
Sir, maybe can you close that third one also a bit faster, sir?
Okay. Actually, sir, I will tell you. See, this is the reference. I have taken 5 example, but that time constraint, so I will show you the reference. You can go for it. This is the reference.
Okay, sir. Done, sir. Done, sir. Maybe I think we can close and we can ask the participant for any questions, if any.
See, actually, it is a very vast subject. Within 2 hours, it may not be that much possible. But I'll try my level best to concise and give everything. I am open. If any doubt, I am ready to clarify it.
Yes, sir. So, dear participants, if you have any doubts, do text in the YouTube chat box. I will try to convey those questions to our speaker, and he can address you. Yes, sir. There is one question from Vinay Kumar. The question is like, hi sir, how to identify the structure of a metal complex which is in semi-solid form, and by which spectra?
We are talking about the simple spectra here. If you have a metal structure, so we can have the we cannot, one spectra cannot say every information. We need to go for, if all spectras are complemented each other. We should see the IR, we should see the NMR, we should see the mass. If we see all three, then only we can have the conclusion. So by keeping one spectra, we cannot have the conclusion, because in the first example also we told that we confirmed with IR, NMR, then later we use the mass. So like that, one spectra we cannot get the conclusion. And which metal, that also will decide, no, which metal, that we can see whether it is IR or NMR or mass.
So Vinay Kumar, please do reply which metal you are using, so that our speaker can help a bit more.
Sir, I will give my mail ID. Let him do that. We will have it. Okay.
Done, sir. Done, sir. Sir, yeah, he replied, sir, it is calcium and copper complexes.
Okay.
One more question, sir.
Yes, sir.
What is the basic difference between LCMS and LCMSMS spectra?
So here we use LC for the separation. The next one we are going for the that means for the again dividing or separating the every fragment. The last MS may be used as a analyzer or the detector. Sir, we get more information about that for a simple LCMS and LCMSMS.
Okay, sir. So you mean that in LCMSMS we will get more information?
Yes.
Okay, sir. Yes, sir. One more doubt asked by Bidyut Dubey. What is the role of relative abundance in mass spectroscopy?
See, as I told that relative abundance is the highly stable cation. So if suppose for example, which cation is highly stable will say about which type of compound is this. Suppose for example, if you take alkane, the highly stable cation, that means we can say that either you may get at 43 or you may get at 57. So that will say about which type of compound is this. Either like that, every compound, the fragmentation pattern is going to be in the unique. That means if you take aldehyde, they are going to fragment in the unique pattern. If you take alcohol, they are going to fragment in the unique pattern. So the base peak will say which type of compound is this, whether it is alcohol, whether it is aldehyde, whether it is a ketone. So that we get the conclusion by keeping the 100% abundance peak.
So one participant asked about the LCMS and MS now.
Yes, sir.
That particular tool is useful apart from identifying the molecular ion peak or molecular weight of the compound. It also helps in identifying and confirmation of contaminants or the residual compound present in the sample.
Okay, sir.
If at all adulterants are present.
Yes, sir. Actually, okay, sir. Okay.
Yes.
Helping, sir. One more doubt by Padmashri KR.
Yeah. Tell me, sir.
Which NMR is better option to confirm the compound, either proton or carbon NMR, or both are required?
Both are required.
Both are required. Please do text in the chat box so that we can get responses from our speaker.
Okay, Prashant.
Yes, sir. Yeah. Thank you for the responses by the participants, and thank you for your active participation and clarifying your doubts. I thank our speaker for giving a great delivery. Now, I would like to ask our HOD, Dr. T.Y. Pasha sir, for giving a few closing remarks. Pasha sir?
Yeah. Thank you, Prashant, for giving me a chance to put a closing remarks for this session of webinar. And in fact, first I appreciate the speaker that very patiently and slowly he took from the basic level to the from UV to mass and to NMR, saying the basic content, how to illustrate and interpret the structure of the molecule if one knows about the molecular weight. And in fact, the as he in the demonstration explained about the index of hydrogen deficiency, uh, my experience says that only the power textbook has given the very good explanation along with the table that if the fifth group or the sixth group or seventh group of elements are added, what to be subtracted and what to be added into the determination of index of hydrogen deficiency. Even I did not get from the Silverstein textbook. And so this is my observation. Thank you, sir, that your patience and very calm and very effective way of convincing the content for the students, sir.
Yes. Thank you, sir.
Over to Prashant.
Thank you, Pasha sir, for your closing remarks. Now, I would like to ask our colleague, Mr. Prakash Kumar sir, for giving vote of thanks.
Yeah. Uh, Good afternoon to one and all. Even on the behalf of our Sri Adin Chinching College of Pharmacy, Adin Chinching University, I would like to extend my heartfelt gratitude to each and every one of you for joining us today for the insightful and emerging webinar. First of all, I would like to thanks for our profound speaker, Dr. A. Prabhar, for his valuable expertise, knowledge, and valuable insight about the interpretation of spectra, which is very important concepts in chemical structure or structural realization. And I would like to express my profound gratitude to our principal madam for her presence in this seminar. And I would like to thank our beloved head of the department for his moral support and guidance for this webinar. And I also happy to express vote of thanks to my coordinator, Dr. Mark Prasan sir, to organizing the good topic webinar for the students as well as presentees. And I express my whole heartfelt thanks for all the sponsoring and participants for joining this webinar and making this grand success. Thank you.
Thank
Okay,
you,
sir.
Prakash sir, for your vote of thanks. Thank you, dear
Thank you, sir.
participants, for attending this live session. Within next few minutes, the feedback link will be there in your YouTube chat box. So please do fill the link so that your e-certificate will be pushed to your mailbox. You can see the feedback link in the YouTube chat box. Thank you.